So today we are going to study chapter 3, that is chemical bonding. So in this chapter we will study about the Vesper theory and shapes of molecules, valence bond theory, molecular orbital theory, and orbital overlapping, paramagnetism, diamagnetism. So all the theories related to chemical and physical properties of molecules. So first of all, we have to study about the electronegativity. Electronegativity is the power of covalently bonded atom to attract the shared pair of electron towards itself. It is a dimensionless property and has no unit because it is only a tendency. So when there is an atom that is highly electronegative and it is with the atom that is not electronegative or electropositive like metal, so the electronegative element will attract the electrons from that electropositive atom. So that is basically the tendency. So it basically indicates the net result of the tendency of atoms in different elements to attract the bond forming electron pairs. We measure electronegativity on several scales. So most commonly used is Linus-Pauling scale. So there are factors that affects electronegativity. Electronegativity is affected by the following three factors. First is the size of atom, second is the nuclear charge, and third is the screening by inner electrons. As the number of protons in nucleus increases, the nuclear charge increases. Hence the size of atom decreases, causing the attraction of bonded electron with the nucleus to increase, resulting in increase of the electronegativity. When the number of inner shell electrons increases, the distance between the nucleus and the valence electrons increases. So the attraction of a bonded electron with the nucleus decreases, causing decrease in electronegativity. So when there are a number of protons adding in the shells, so the electron charge is increasing. So as the size of the atom is increasing, so there is a decrease in the attraction of the bonded electrons with the nucleus. So electronegativity increases. That is the general trend. And when the number of inner shells electron increases, the distance between the nucleus and the valence electron increases, so the attraction of the nucleus with the bonded electron decrease. Therefore there is a decrease in the electronegativity. So here's the table in which the Pauling electronegativity values are given. For hydrogen it is 2.20, for boron is 2.04, carbon 2.55, for nickel 3.04, oxygen 3.44, and fluorine has the highest electronegativity, that's it's 3.98. So these are the basic electronegativity values given by Pauling scale. Now what is the trend of electronegativity in the periodic table? So electronegativity decreases from top to bottom in groups. So there is increase in the atomic number as we move down the group in the modern periodic table. The nuclear charge also increases, but the effect of increase in nuclear charge is overcome by the addition of an extra shell. The attraction of shared electron with the nucleus decreases, hence the value of electronegativity decreases. So basically the electronegativity decreases from top to bottom because of the increasing size. When the size is increasing, so electronegativity decreases. For example, in the halogen from fluorine to astatine, electronegativity value decreases. So electronegativity increases in a period from left to right, and this is due to the high effective nuclear charge. Shielding effect remains constant and the size of atom decreases, and the nucleus got more power to attract the bounded electrons. For example, in the third period from sodium to chlorine, the electronegativity value increases as it is shown in the figure. Now we are going to study about the nature of bond in terms of Pauling electronegativity values. So if the value is more than 1.8, the electronegativity value is more than 1.8, then the bond will be ionic. And if it is between the 1.8 and 0.4 and 1.8, so the bond will be polar covalent. And if the electronegativity value is less than 0.4, then the bond will be non-polar. So now we will consider some examples, like we are considering the example of oxygen molecule. So the oxygen has electronegativity value 3.44. So each atom will have the electronegativity of 3.44. So the difference will be 0, which means that none of the two atoms in the molecule pulls the electron. So because they both have the same electronegativity value, so the resulting bond will be covalent bond. And it will also a non-polar covalent bond because the electronegativity value is 0, that is less than 0.4. So this compound has next one is a potassium chloride. So this one has the electronegativity 0.82 for the potassium and 3.16 for the chlorine. So obviously the chlorine is more electronegative and it will attract the electrons from the potassium. So the difference between them is 2.34, which is obviously greater than 1.8, and the bond will be ionic. So we can also use the electronegativity differences to predict the bonding nature of the molecule. This molecule consists of hydrogen atom. Third one is the hydrogen chloride. So it contains hydrogen and chlorine. So hydrogen has electronegativity of 2.20 while chlorine has 3.16. So chlorine is more electronegative than hydrogen. So the difference is 0.96, which is between 1.8 and 0.4. So the bond will be polar covalent bond. Covalent character in a compound. Covalent character in a molecule depends upon the polarizing power of the cation, which in turn depends on the oxidation state of cation. Higher the polarizing power, the more will be the covalent character. So what is the polarizing power? Polarizing power is basically the distortion of the electronic cloud. So it all depends on the oxidation state. So when we move from left to right in a period, covalent character increases. For example, aluminum chloride is more covalent in nature as compared to magnesium chloride. So because the aluminum chloride is the oxidation state of +3 while magnesium has the +2, so the electronic cloud of the aluminum chloride is more polarized. So it has a high polarizing power. So it can polarize the anion, causing electron to be shared between the two ions. Hence, covalent character will be developed in the compound. What is dipole moment? It is a product of the magnitude of positive and negative charges and the distance between them. Mathematically, it can be written as dipole moment is equal to Q dot R, that is charge into separation distance. SI unit of dipole moment is debye, and 1 debye is equal to 3.335 into 10 to the power minus 30. So it's simply a product of positive and negative charges. And Cm stands for Coulomb meter. The difference between the electronegativities of two atoms in a compound determines the overall dipole moment and overall polarity of the compound. Like HCl. In HCl, the dipole moment has a magnitude and a direction, and the arrow will be towards the more electronegative atom. Electronegativity difference between the two atoms determines the bond polarity of the molecule. Greater the electronegativity difference between the two atoms, more will be the bond polar, means more ionic nature. But a small difference in electronegativity, it will just make a bond polar or more covalent in nature. Now, what is polar and non-polar covalent bond? In polar covalent bond, due to electronegativity difference, one atom which is more electronegative will attract shared electron to itself and bear partial negative charge, and the other one bears partial positive charge. Such molecules are called polar molecules. Polar molecules have dipoles, electric charges of equal magnitude and opposite sign. Like we have the example of NaCl. So NaCl is basically, it has a polarity. So it's an ionic compound. Symmetrical polyatomic molecules like non-polar molecules have shape of linear, trigonal, planar, and tetrahedral. In these molecules, dipole of bond exerts equal and opposite effects. Hence, they cancel the charges. Non-polar have no overall charge. So, for example, we have the example of CO2. CO2 has zero oxidation state. It has no overall charge. So net pole moment, we can see here that it's 0.7 minus 0.7, which is equal to 0. Due to electronegativity difference between carbon and oxygen, C double bond O bond in CO2 is polar, but CO2 is non-polar because dipole gets cancelled each other. So C double bond O is a polar, but the overall the molecule, that is CO2, is non-polar in nature. Now we will talk about the bond energy, that is bond enthalpy. So the energy which is required to break the bond of the same type in 1 mole of a substance is known as bond energy. So the energy which is required to break the bond in 1 mole of a substance, and it is represented by the kilojoule per mole, that is unit. Now the electronegativity difference, it depends on the electronegativity difference between two bonded atoms, size of the atom, bond order and bond length. The greater the electronegativity difference between two bonded atoms, the more polar will be the bond and greater will be the bond energy. For example, we have the example of HF that has bond energy 562, then HCl 431, then HBr 366, and HI that has 299, because the electronegativity difference between them is in this order, like HF has 1.8, HCl 0.9, then 0.7, 0.4. So the bond energy, more the electronegativity difference, more the bond energy. Now we will talk about the bond length, that has a little bit of different criteria or trend. Bond length is the distance between the nuclei of two covalently bonded atoms. It is measured and in a Amston knot and or the picometers, that is 10 into minus 12 meters. Bond length depends upon the size of atom. Smaller the size, the greater the bond energy, and the shorter the bond length. Bond energy of HH is 436 and of HBr is 366. It is due to shorter bond length of the hydrogen molecule compared to HBr. So we will look at this table, that is fluorine bond energy is 158 and bond length is 149. Now we have ClCl that has bond energy 242 while the bond length is 199. So fluorine has a small size, so its bond length is less than the chlorine. The bond energy is also less than the chlorine because of the repulsion of the lone pairs of fluorine. Then we have the bromine that has bond energy 193, bond length 228, then 151 and 266. So you can see that as the bond energy is decreasing, the bond length is increasing. But we have the exception for the fluorine. Its bond length is less, but its bond energy is also less due to the lone pair repulsions. The atomic radius increases from fluorine to iodine, bond energy decreases from chlorine to iodine, but fluorine molecules have low value of bond energy. It is because of the smaller size of fluorine and that their lone pairs repel each other, hence less amount of energy is required to break the bond. Bond energy is also used to predict the reactivity of covalent molecules. Greater the bond energy, stronger will be the bond, and that molecule will be stable and less reactive. For example, alkyl halides and alkyl fluorides are less reactive than alkyl chlorides, as the bond energy of CF is greater than CCl. So the bond between the CF has a high bond energy and the molecule will be stable and least reactive. Now we have the shapes of molecules, and we are going to study the VSEPR theory, that is valence shell electron pair repulsion theory. This theory is basically used to determine the shapes and the bond angle. So this was the first concept regarding the chemical bonding, the theories regarding to chemical bonding and shapes of the molecules. So the electrons are negatively charged, they repel each other, and pair of electrons are bounded by some central atom. So that if there are different shapes and bond angles that they exhibit, and it will depend on the number of pairs of electrons, lone pairs, bonding pairs. So lone pairs are those that have more concentrated electronic cloud than the bonding pairs, and these are those pairs that don't take part in a chemical reaction. So they're in the bonding. So their cloud charges are wider and slightly closer to the nucleus. This results in a different amount of repulsion. So the lone pair has a very important role in determining the shape and the angle. Basically the angle, the lone pair affects the angle of the molecule. So if there are greater lone pairs, there are many lone pairs, I mean 1, 2, 3, so the bond angle will vary according to that. So the order of repulsion in lone pair, most repulsion, okay, then lone pair, then bond pair, and bond pair has the least repulsion. So there are shapes of molecules containing 2 electron pairs. So those molecules where central atom is surrounded by 2 electron pairs and no lone pair has a linear shape and an angle of 180. Like we have the example of AX2 like BeF2. It has 2 valence electrons, and for the beryllium, that is the central atom, and it has fluorine atom that contributes 1 electron from each side. So 2 electron pairs around the central beryllium atom. See from the above figure the arrangement that minimizes repulsions, places the groups 180 degree apart. Now we have the shapes of molecules containing 3 electron pairs. Those molecules where central atom is surrounded by 3 electron pairs and no lone pair. Okay, so we have the geometry that is trigonal, and the angle will be 120 degree. The central atom is boron that contributes 3 valence electrons, and each chlorine atom contributes 7 electrons. The Lewis electron structure and shape of BCl3 is shown. So there are 3 electron pairs around the central atom, so that to minimize the repulsions, so the groups are placed 120 degree apart, and geometry is trigonal planar. In carbonate ion, so we have the CO3 2-, the central atom carbon has 4 valence electrons, and each oxygen atom has 6 valence electrons. There are 3 bonding pairs around the carbon. The geometry of CO3 is trigonal planar as well. Okay. Now we have the 2 bonding pairs and 1 lone pair. Like we have the structure of SO2. Sulfur has 6 valence electrons and 2 double bonds and 1 lone pair. So the angle will be 120, but the shape will be called V-shaped or bent. And it is because of the presence of a lone pair. Now we have the shapes of molecules that contain 4 electron pairs. So the geometry will be the tetrahedral, like in we have the example of CH4. So the geometry will be tetrahedral and the shape of and the angle will be 109.5 degrees. And if we have the 3 bonding pairs and 1 lone pair, as in the case of NH3, so we have the angle of 107 degrees and the shape is trigonal pyramidal, like we can see in this figure. Due to the presence of lone pair, the angle gets smaller. Now we have 2 bonding pairs and 2 lone pairs, like in the example of water. Water has also bent shape and the angle between the oxygen and hydrogen is 104.5 degrees, and this is due to the presence of 2 lone pairs. Now we have the shapes of molecules containing 5 electron pairs. So there are some cases, like we have the case of phosphorus pentachloride, and it has 5 electron pairs, no lone pair. So it has the shape trigonal bipyramidal. And the bond angles of chlorine and phosphorus is 120 degree, and between the 2 chlorines the angle is 90 degree. Now shapes of molecules containing 6 electron pairs. So in 6 we have the angle 90 degree, and it is basically the octahedral shape. Now we have the expanded octet, that is hypervalency. The octet rule applies well to the atoms in the second row of the periodic table. So if there is an electronic configuration will be S2p6. Even elements in the third and fourth row are known to follow this rule. But some cases, when there is addition of subshells like D, F and G subshell, so atoms of 3 and 4 period can have higher valence shell counts by expanding into additional subshells. When atoms contain more than 8 electrons in their valence shell, they are said to be hypervalent, and this is known as the expanded octet. Like we have the example of SO4, NO3, PO4, so they have the expanded octet. Now we have the summary of shapes of molecules. Okay, you can see the number of valence electrons 4, number of bonding 2, and number of lone pairs 0. So total number of electron pairs 2. So the arrangement will be linear, has an angle 180 degree, and the examples are BeCl2, HCN and CO2. When we have the number of electrons 6, bonding is 3, lone 0 and electron pairs will be 3. So the geometry will be trigonal planar. So there will be the angle that is 120, and the examples are BF3, AlCl3 and NO3. Now we have the number of valence electrons 8. So they have okay, I skipped this. Okay, when there are bonding electrons are 2 and the lone pair is 1, then the total electron pairs will be 3. The geometry will be bent 118. The example is SnCl2. Now we have the 4 bonding and 0 lone pair. The geometry will be tetrahedral like in CH4, SiCl4, SO4, NH4. Angle will be 109.5. If we have 3 bonding 1 lone pair, then trigonal pyramid 107, NH3, PCl3 and ClO3. And if we have the bonding pair 2, lone 2, then the geometry will be bent like in the water and in the hydrogen sulfide 104.5 degree of the angle is also present. Now we have the 5 bonding pair, no lone pair, then trigonal bipyramid 90 degree and 120 degree angle. Example is PCl5, Pi5. And if we have the 6 bonding electron pairs, no lone pair, then the geometry will be octahedral, and that is 90 degree for the SF6 is the example. So this is the basic chart. So you can see that again that 2 bonding pairs linear geometry, 3 bonding pairs trigonal planar, 2 bonding and 1 lone pair has bent, 4 bonding pairs tetrahedral, 3 bonding and 1 lone pair trigonal pyramid, and 2 bonding and 2 lone has bent geometry. 5 bonding and 6 bonding have trigonal bipyramid and octahedral respectively. Now we are going to study about the working out the shapes of molecules. So here we are going to take 2 examples, example 1 and example 2 in the geometry of NH3. Valence electron of nitrogen is 5. So electron from the 3 chlorines are 3. Total number of electrons 8. Number of electron pairs 4, because 2 electrons make a pair, so 4. So the electron pairs are arranged tetrahedrally. Number of the atoms surrounded the central atom is 3. Number of bonding pair 3 and a number of lone pair 1. So this molecule is trigonal pyramidal. Now we have the geometry of NH4 plus, 1 plus. Valence of nitrogen 5. Electron from 4 hydrogen 4. Charge is 1 plus. Total number of electrons 8, so pair are 4. We have to arrange them tetrahedrally. Number of atoms, because number of atoms are surrounding the central atom of 4, there is no lone pair, so the geometry will be tetrahedral. Now we are going to study the last topic for the today. That is the importance of Vesper theory in the field of drug. By predicting molecular shapes and bond angles, Vesper aids medicinal chemists in understanding how drug molecules interact in the body. Shape and dimensions of the molecules being used as drugs also depend upon the length and angles of the bonds. Any change in bond angle affects the overall 3D shape of the molecule and thus affecting their binding ability or permeability through membranes of target cells. Molecular shape and enzymatic reactions. Enzymatic reactions. So enzymes recognize and bind to drug substances based on their molecular shape. Vesper helps to predict this 3D structure, allowing designers to tailor molecules for optimal interaction with the enzyme's active sites. Understanding the molecular geometry through Vesper aids in creating drugs with enhanced substrate recognition, facilitating targeted interactions in enzymatic reactions. So basically we can predict the shape of the molecule and we can mold that molecule in the shape that is most effective in the body. that can interact with the enzyme's active sites. So, enzyme substrate interaction in drug design. Consider the interaction between a drug and enzyme acetylcholinesterase in neuropharmacology. Vesper guides the design of drugs with shapes that fit precisely into the enzyme active sites, enhancing efficacy and specificity. Molecular geometry in drug delivery system. Vesper theory, which predicts molecular shapes and plays a vital role in designing effective drugs carriers, liposomes, spherical lipid-based vesicles, are extensively used as drug carriers due to their biocompatibility and versatility. Vesper informs the design of liposomal carriers by predicting the optimal arrangement of electron pairs, influencing their three-dimensional structure. For instance, tailoring liposomes in specific shapes such as elongated or targeted geometries enhance their ability to navigate biological carriers and efficiently deliver drugs to the desired tissues. So liposomes are basically used as drug carriers. So they are basically influencing the three-dimensional structure. So they have the elongated or targeted geometry. So they can easily bind to the desired tissues. Now imagine a drug molecule designed to interact with a specific enzyme. The Vesper-derived geometry of this drug molecule needs to be considered to ensure optimal binding. If the enzyme active site is a pocket with a tetrahedral arrangement of the binding site, a drug with a complementary tetrahedral geometry might fit more effectively. So the drug has the design that fits its active site. Understanding molecular geometry also helps scientists to understand the shapes of the more complex molecules like protein and DNA. The shapes of these molecules play incredibly important roles. Cisplatin is a neutral complex, that is platinum NH3 2Cl2, and it is known as the cisplatin. It has a square plane structure, and it is used as anti-cancer agents in the treatment of solid tumors. It is generally considered a cytotoxic drug which kills cancer cells by damaging DNA and inhibiting DNA synthesis. Cisplatin-induced DNA damage activates the various signaling pathways to prevent or promote cell death. Thank you so much.